In the vast darkness of space, a single galaxy burns bright enough to rewrite everything we thought we knew about cosmic history. This galaxy existed when our universe was barely 290 million years old, just 2% of its current age. But this ancient light carries secrets that challenge our deepest theories about how galaxies form, how quickly stars can ignite, and whether the universe itself might be hiding inside something unimaginably vast. From impossible brightness to missing black holes, from chemical fingerprints that should not exist to theories that place our entire reality within a cosmic prison. Prepare yourselves. We begin. Music. Deep in the constellation Forix, astronomers discovered something that should not exist. The galaxy burns with the light of hundreds of millions of suns. Yet, it formed when the universe was barely out of its infancy. Named Jade's GSZ 140, this cosmic lighthouse shattered every distance record we had ever set. At a redshift of 14.32, it dates back to less than 300 million years after the Big Bang, pushing our view deeper into time than ever before. To understand how extraordinary this discovery truly is, picture the universe as a 13-year-old child. This galaxy would have existed when that child was barely 3 months old. The light we see today began its journey across 13.5 billion years of expanding space. Stretched and reamed are the universe's own growth. The James Webb Space Telescope observed this galaxy for almost 10 hours using its near-infrared spectrograph. And when scientists first processed the spectrum, they knew they were looking at something unprecedented. The previous record holder, another galaxy discovered just years earlier, suddenly seemed almost modern in comparison. But distance alone was not what made this discovery so startling. Jade's GSZ 040 is over 1,600 light-years across, proving that the light we see is coming mostly from young stars and not from a mission near a growing supermassive black hole. For a galaxy this early in cosmic history, such size defies our expectations. Imagine trying to build a massive city in just the first few days after breaking ground on an empty plot of land. That is essentially what this galaxy accomplished in cosmic terms. The building blocks of matter had barely had time to cool and clump together when this galaxy was already blazing across the early universe. The source was surprisingly bright, which we wouldn't expect for such a distant galaxy, astronomers admitted. In the infant universe, galaxies should be small, faint, and struggling to form their first stars. Instead, this ancient giant glows with an intensity that rivals much younger, more mature galaxies we observe in our cosmic neighborhood. The discovery forced scientists to question fundamental assumptions about galaxy formation. How could something so massive and luminous exist so early? What processes could have assembled so much matter and ignited so many stars in such a remarkably short time? Its age, size, and luminosity added to a growing body of evidence that current theories of early star and galaxy formation are incomplete. This single point of light in the darkness was telling us that the early universe was far more active and dynamic than our models had predicted. As we peer deeper into the cosmic past, each new discovery chips away at our confidence in how well we understand the universe's earliest chapters. But this galaxy's shocking brightness was only the beginning of its mysteries. At the heart of most luminous galaxies lies a monster that feeds on matter and shapes entire galactic neighborhoods. When astronomers split the light from Jade's GSZ 140 into its component wavelengths, they uncovered a chemical signature that challenged everything we knew about the early universe. The galaxy was rich in nitrogen, unusually rich for such an ancient object. This discovery was like finding a sophisticated wine cellar in a house that was supposedly built yesterday. Nitrogen is not a primordial element that existed at the universe's birth. Instead, it must be forged inside stars and scattered into space when those stars die. Jake's analysis indicates that the brightness of the source implied by a mere observation is above what would be extrapolated from the measurements by the other Webb instruments, indicating the presence of strong ionized gas emission in the galaxy in the form of bright emission lines from hydrogen and oxygen. But nitrogen presented an even deeper puzzle. In the cosmic timeline, hydrogen and helium were the only elements present after the Big Bang. Every other element from carbon to iron to nitrogen had to be manufactured inside stellar furnaces over millions or billions of years. Stars live, burn through their nuclear fuel, and die, scattering these newly created elements into space where they can be incorporated into the next generation of stars. This process takes time, lots of time, for a galaxy to be nitrogen-rich just 290 million years after the Big Bang. Multiple generations of massive stars would have had to live entire life cycles, die in spectacular explosions, and seed the surrounding space with their chemical products. Imagine trying to find evidence of great-grandparents' recipes in a cookbook written on the day a family first settled in a new country. The presence of complex refined ingredients would suggest that many generations had already passed, even if the official records claimed otherwise. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that M01Z14 is forming stars in extremely dense environments. The connection between this ancient galaxy and the oldest stellar populations in our own cosmic neighborhood implied that rapid, intense star formation was occurring under conditions we had not fully understood. The nitrogen abundance pointed to what astronomers call chemical evolution, happening at an accelerated pace. Normally, this process unfolds over billions of years as successive generations of stars gradually enrich their surroundings with heavier elements. But JADE's GS-140 appear to have compressed this timeline dramatically. That means galaxy evolution may have started much earlier than we thought. If massive stars were forming, living, and dying fast enough to produce significant nitrogen enrichment within the first few 100 million years of cosmic history, then the universe was far more active in its youth than our models predicted. The chemical fingerprints suggested that this galaxy was not a pristine first-generation object, but rather the product of an already complex stellar ecosystem. But even as astronomers struggled to understand how such rapid chemical evolution was possible, they were about to discover that this galaxy was not alone. JADE's GS-140 was supposed to be an impossible outlier, a cosmic fluke that defied all expectations about the early universe. Instead, it opened the door to a much larger mystery. Given the relatively small region of the sky that we searched to find Jesus GS-140, its discovery has profound implications for the predicted number of bright galaxies we see in the early universe. If such luminous objects could be found in a tiny patch of sky, how many more were waiting to be discovered across the vast cosmic landscape? Think of it like finding a bustling city while exploring what you thought was an empty wilderness. The discovery would immediately raise questions about how many other cities might exist in unexplored regions. Astronomers faced a similar situation as they realized that bright early galaxies might be far more common than anyone had imagined. Since its science observations began in July 2022, the JADE-OST has discovered a series of increasingly distant ancient galaxies. Each new discovery pushed the boundaries further back in time, but also revealed that the early universe was populated with objects that should not have existed yet. The James Webb Space Telescope had only surveyed a minute fraction of the entire sky. Yet, it was consistently finding these bright ancient galaxies. Statistical analysis suggested that there could be hundreds or even thousands of similar objects scattered across the cosmic deep field, each one representing a challenge to our understanding of early galaxy formation. Astronomers have used data from NASA's James Webb Space Telescope early release observations and discovered 87 galaxies that could be the earliest known galaxies in the universe. This growing population of ancient bright objects was rewriting the cosmic census. Previous models had predicted that early galaxies would be small, faint, and rare. The universe should have been a relatively quiet place in its first few 100 million years, with star formation proceeding slowly and inefficiently. Instead, astronomers were finding evidence of vigorous stellar nurseries operating at full capacity when the cosmos was still in its infancy. These ancient bright galaxies sometimes called little red dots, are popping up across JOST's surveys. The nickname little red dots came from their appearance in early telescope images, but these objects were proving to be anything but insignificant. Each new discovery added weight to the growing realization that the early universe was far more active and structured than theoretical predictions suggested. If bright galaxies were common in the cosmic dawn, it meant that the processes of star formation, element creation, and galactic assembly had proceeded much more rapidly than anyone thought possible. It is likely that astronomers will find many such luminous galaxies, possibly at even earlier times over the next decade with Webb. The James Webb Space Telescope was just beginning to explore the deepest reaches of space and time. As the evidence mounted for a universe that was bright and active from its earliest epochs, astronomers began to wonder if they had fundamentally misunderstood something about cosmic evolution itself. The next discovery would suggest that the problem might be even deeper than anyone imagined. Every major scientific theory rests on a foundation of carefully constructed models that predict how the universe should behave. When observations consistently contradict these predictions, scientists face a fundamental choice: modify the models or question whether something deeper is wrong with our understanding of reality itself. Current theories of early star and galaxy formation are incomplete. The discovery of Jade's GS Z140 and its bright companions was forcing astronomers to confront this uncomfortable truth. Decades of theoretical work had painted a picture of gradual cosmic evolution, but the universe was revealing a much more dramatic and rapid development. The spectroscopic confirmation of this source indicates the existence of many similar galaxies, particularly when considering the relatively small survey area of Jade. This was not just one anomalous object that could be explained away as a special case. It was evidence of a systematic underestimation of how quickly the early universe could assemble complex structures. Consider a computer simulation designed to predict how a city will grow over time. If the simulation consistently predicts slow, gradual development, but satellite images reveal massive skyscrapers appearing in just the first few months, the underlying assumptions about construction rates and urban planning would need to be completely reconsidered. Cosmological models faced a similar crisis. The halo mass threshold required to yield a fixed cooling abundance varies as the inverse 6th power of 1 plus redshift for this region of mass and redshift. In simpler terms, the dark matter structures needed to host such massive galaxies should have been extremely rare at such early times. Dark matter halos provide the gravitational scaffolding upon which galaxies form. These invisible structures must grow to sufficient size before they can begin efficiently converting gas into stars. According to standard models, the early universe should not have had enough time to grow halos massive enough to support the bright galaxies Webb was discovering. GSC 140 represents a fascinating yet very challenging test case for the scenario that astronomers had developed to explain galaxy formation. The galaxy exhibited properties that stretched multiple theoretical frameworks to their breaking points. The crisis extended beyond just galaxy formation models. If the early universe was more structured and active than predicted, it might indicate problems with our understanding of dark matter, dark energy, or even the fundamental physics governing cosmic expansion. If galaxies like MONZ14 existed in greater numbers, formed stars faster, and were chemically richer than we thought possible, what else are we missing? This question hung over the astronomical community like a storm cloud, suggesting that the discoveries might be symptoms of much deeper misunderstandings. Some theoretical physicists began to propose radical solutions. Perhaps the universe itself was not what it seemed to be. Perhaps the very stage upon which cosmic evolution played out was fundamentally different from what we had assumed. The next chapter of this story would take us beyond conventional astronomy into realms where reality itself might be questioned. But first, we needed to understand what these discoveries meant for the future of cosmic exploration. The discovery of Jade's GS 140 marked the beginning of a cosmic treasure hunt that would reshape our understanding of the universe's earliest chapters. Kartal, Hanin, and Robertson agree that Jodorowsky's power has not yet reached its limits. None of them would be surprised if the telescope unveils a new redshift record within the year. The James Webb Space Telescope was operating like a time machine, systematically pushing back the boundaries of observable cosmic history. Astronomers realized they were standing at the edge of a new frontier. Every observation session brought the possibility of finding even more distant, even more impossible galaxies. This specific area Jade has been studying is pretty small. There are larger areas of the sky that have yet to be explored that maybe have even brighter and more distant galaxies. Picture archaeologists who had spent decades carefully excavating what they thought was a small ancient settlement, only to discover that they were standing on the edge of a vast buried metropolis. The scope of their task had suddenly expanded beyond anything they had imagined. Jade's GSZ-14Z was the record holder at a redshift of 14.32. But now it has found another ancient bright galaxy at redshift Z equals 14.44. Less than a year after the first discovery, an even more distant galaxy had been confirmed, pushing the cosmic frontier back by another 10 million years.